We're going to talk about vectors today, and we're going to extend. We've already talked about a little bit about vectors, so we'll review what we already said about vectors. But we're going to extend vectors into two-dimensional space today, so things are going to get a little more complicated. We'll talk about a little bit about vectors and scalars, coordinate systems. When I say coordinate systems, I'm talking about either using rectangular coordinates or polar coordinates. And then we'll talk about some properties of vectors, for vector addition, subtraction, and so on. Okay, now we already have talked about vectors a little bit. Let's review a bit. We talked about, motion along a single axis, and we said that, hey, look, if I've got an axis here, we'll put 0 here. And we'll say this is the position axis in meters. We said that if an object is located in space somewhere along the single dimensional space, let's say the object is right here, we would say that, maybe this will be the initial position. We'll say the x initial is equal to 3 meters. Now, because we said it's positive 3 meters, what that means is that as measured from the origin, it's located over here. And notice that I could draw that as an arrow, right? And then maybe the final position is over here. So maybe I can say x final is negative 2 meters. And so we have a magnitude of this thing, 2 meters. It's 2 meters away from the origin. But we also have a direction on that number line, and that's indicated by this negative. And what the negative means is, hey, it's to the left of the origin. Then, of course, we had our displacement vector, delta x, and that was x final minus x initial. And if x final is negative 2 meters minus 3 meters, well, that gives us negative 5 meters. That's our displacement vector. And our displacement vector starts at our initial position of 3 meters and goes to the left by 5 meters. So we've already been dealing with this idea of vector, where this is a quantity where to completely specify the quantity, you have to say how big it is, its magnitude, and what direction it's in. And the direction it's in, if you're dealing with one-dimensional motion, we usually say, is it in a positive direction or a negative direction? If it's positive on this number line, it's to the right. If it's negative, it means to the left. So, and then when we were dealing with free fall problems, if you were dropping an object and it was falling down, usually we said, okay, we'll make down negative and up positive. And so the direction of it was pretty easy to deal with, right? Because it was either to the left or the right, or it was up or down. But of course, objects don't exist in one-dimensional space, thank goodness. How would we get around each other if space was just one-dimensional? We just run back and forth on our little spot on the number line, bouncing around. We obviously live in a three-dimensional space, and we're not going to get to 3 dimensions yet. Let's take baby steps. Okay, we've done one-dimensional space. Now we're going to go to 2-dimensional space, and then we'll get to 3 dimensions here soon enough. So in 2-dimensional space, what we're going to have to do is create a coordinate system. for position. If an object is located on a two-dimensional space, we need two axes. It's traditional to call this the x-axis and this the y-axis, at least in physics. Quite often when you draw it like this, this will be x and this will be z, and then y comes out. It all depends on the book you're using and who the author is, but this is what we're going to do in physics. And let's say an object is located right here. Well, we have to find some way of communicating where this is with respect to the origin. I mean, that's position, right? And you could draw an arrow like this. So one way of specifying where it is say, okay, how far away is it? That's the magnitude of this arrow, this position arrow, and what direction it's in. Well, to specify the direction, we have to kind of all agree that we're going to pick a place to measure the angle from, right? And so what we're going to do is we're going to measure the angle from the positive x-axis. And so this is going to be my angle. And what I'm going to call the magnitude of this position vector, I'm going to call this r. So my position at that location in space, I can specify it, and I'll specify it with an r vector like this, this little r with the vector head on it. And I'll say, okay, look, r has a magnitude. This vector has a magnitude. We'll call that r. So usually we put the magnitude first, and then we put the angle. And I think you've all done this before in your math classes. This is called a polar coordinate, and it just gives a magnitude and a direction. But there's another way to specify r. We can specify it with saying, okay, how far do I go in the x, and then how far up do I go in the y? And that'll work just as well. So I can specify r, well, this is let's go ahead and label it. This is a polar coordinate. And then I can have what's called a rectangular coordinate. And a coordinate is just a couple of numbers that tell you everything you need to know about where something is on a certain space. Now here we deal with two-dimensional space. Well, we were dealing with one-dimensional space up here. Now we're dealing with two dimensions. You have three-dimensional space. And then in certain applications, you can have multiple dimensional spaces. Those spaces don't have to be like, the 3 dimensions of space we're dealing with. But anyway, that's for you to study sometime in the future. And what we can do is say, hey, look, r is going to have an x value. We'll call that r in the x. That's kind of its x component. That's called an x component. So r in the x, and then we'll say that this is how far it goes up. This is r in the y. So this does tell me everything I need to know. I can get I know exactly where this object is located in space if I tell you how far you go to the right in x and how far you go up in y. And this will work on the whole plane, right? I'm just showing the the first quadrant here, but this will work for any quadrant. Same with this. Your angle can be greater than 90 degrees and go all the way around. Okay? Now, what we want to do is relate these two coordinate systems. And as you know, from your math classes. We have certain ratios that we've defined that your calculator has programs in it to figure out what the ratios are. The y and the x components, well, they are orthogonal, right? They're perpendicular to each other. That is, they form a right angle. And so you can see that this position vector with its x and y components forms a right triangle. So we can use the mathematics of right triangles to locate objects in space. And we're going to, basically, we're going to relate r and theta, rx and ry this way. And so, since we have a right triangle, I mean, the most fundamental equation for right triangles is the Pythagorean Theorem. And so, a little bit. So let's go with the Pythagorean Theorem. I think I'm pronouncing that right. So you say, well, r is equal to the square root of the x component squared plus the y component squared. And so this gives me, if I give you the rectangular coordinates, you can use this to figure out the magnitude of the whole thing, how long this is right here. Now the angle is a little trickier. Well, first of all, let's review, before we get to that, let's review our trig functions. And let's do that down here. If I have a ratio, I mean, we have all the ratios, right? And we have ry over rx. That is this length divided by this length. And this ratio is called tangent theta. I mean, this is the definition of tangent theta. You take ry divided by rx. By the way, this works even if ry or rx, if you're in another quadrant and they're negative. Okay, this works. Then we have ry over r. That is this opposite leg of this triangle divided by the hypotenuse here, or the magnitude of r. And this, by definition, is called sine theta. And you all know this. And then we have the rx over r. By definition, is called cosine theta. And these are the ones that we're going to use in this class. Tangent, sine, and cosine. Of course, you have the reciprocals of these. You could just go, well, what is rx over ry? Well, by definition, that's cotangent theta, but we almost never use it in this class. We have r over ry. That's called cosecant theta, I believe, right? Is it sometimes I get cosecant and secant mixed up. R over Rx is secant theta. But we don't use these ratios very much. But we do these. Now, the cool thing is that these ratios, the ratios stay the same no matter how big this right triangle is, as long as you keep that angle the same. In other words, if I made the right triangle bigger, Rx is bigger, Ry is bigger, and R is bigger, but they're all proportionally bigger. If I made this twice as big, then this will be twice as big, and this will be twice as big, so when I do the ratios, I get the same answer. That's kind of the foundation of trigonometry. So anyway, we can take this expression and we can solve it for the angle. In other words, here's what we do. You give me the angle, I'll give you the ratio of Ry over Rx. But if you give me the ratio of Ry over Rx, I can give you the angle by using the inverse function. equals the, thank you. I can use this. I can say theta is equal to the inverse tangent of ry over rx. Okay. Now, what this is saying is, hey, look, I'm going to use, you give me the ratio of ry over rx, I'll tell you what the angle is. Okay. So this is a way, if I give you the rectangular coordinates and I want the polar coordinates, these are the two equations I would use. So this goes from rectangular to polar. Okay? Coordinates. There is a problem with this, though. Your calculator is kind of stupid. And that is, if you look at this, here are your coordinates. Here's coordinate 1, 2, 3, and 4. If I have something like this, let me zoom in. Now here, my x and my y are both positive. But so when I plugged in this ry over rx, I get a positive ratio, and your calculator has an algorithm that says, okay, there's your angle. But what if I'm over here instead? What if I'm in the opposite direction? Here x is negative, and here our y is negative. Well, what's a negative divided by a negative is a positive, right? So if y if your ry is negative and your rx is negative, the negative will cancel, and it'll give you the wrong angle. Your calculator will. It'll give you the positive angle. It'll think that you're over here. So what do you have to do to get the correct angle if you're going to measure the angle from the positive x-axis? If we want to measure the angle in polar coordinates, we want to measure the angle from the same place. You have to add 180. Now, if you do this, what if what if you have negative y but positive x? Your calculator can handle that. It'll say, okay, cool. Your y is negative. This is positive. You'll crank it in to your calculator. Most of you have calculators that will give you the negative angle, like negative 30 degrees or something. And that's great. And you can write it that, or you could, add that negative angle to 360 and get, the positive version of that angle. I don't care. But what happens if your xy coordinates are over here? Here you have positive y but negative x. Well, a positive divided by a negative is the same. It has the same sign as a negative divided by a positive. It's ambiguous. Your calculator is just going to say, hey, look, I'm just dealing with this, okay? I'm not going to deal with quadrant 2. I'm just going to give you quadrant 1 or quadrant 4. You got to figure out the rest. So it'll tell you like negative 30 degrees. If you're over here, it'll think, no, you're down here. But then what do you have to do to get over here? You have to add 180 degrees to it. Yes?
So basically for this unit, if we were trying to find the angle, basically the angle you want us to find is always from the positive side of the x-axis. It's not just linear x-axis.
Exactly. Perfect. When you're in polar coordinates, the angle is always going to be measured from the same place. Otherwise, it's confusing when you're dealing with, like a position. It's just a lot easier in the long run to say, hey, all the angles are measured from the positive x-axis. Okay? And then everybody knows what they're talking about. So what I'm going to do is this. I'm going to add to this equation. I'm going to add 180 degrees if what is true? Yeah, if you have a negative x. If negative r sub x. If the component of the x component of your position vector is negative, then you're going to have to add 180 degrees to whatever answer your calculator gives you. Because it is, if you just use the inverse tangent button on your calculator, it's not smart enough to do that. Now, some of you might have rectangular to polar or polar to rectangular functions on your calculator, and it will take care of that for you. So you kind of have to be, careful. You kind of have to visualize, and visualize the vector to know kind of where it is, where it should be, and then check that with what your answer is. Okay, now to go the other way, to go from polar to rectangular, it's a lot easier and it's less ambiguous. I mean, you don't have that inverse tangent problem. We know that sine of theta, by definition, is ry over r. So if I give you r and theta, I just solve this for ry. R sine theta. And this works for any angle. So you just take this and solve it for r. I mean, solve it for rx. So if I give you r and theta, I just use these two equations to convert from, this is from, I give you polar, you want to convert it to rectangular. Okay, so it's pretty easy. Just use the sine and the cosine stuff. All right, now let's talk about angles for a little bit. And I know this is, again, all of this should be, hopefully, as review for you. We have two ways of measuring angle that we're going to use in here. Well, actually, three ways, but let's talk about two of them right now. We have degrees and we have radians. Now, a radian, well, okay, let's go to our circle here, like the good old unit circle. You know, I still have not mastered the ability to make a good freehand circle by writing. When I used to do all my lectures on a whiteboard, I was famous for just being able to whoosh, make an awesome circle. So it's kind of lopsided. Sorry. Now we have an angle, and we know, okay, from here to here, we break this up into 90 little wedges. I'm not going to draw all 90, but 90 little wedges, right? And so this would be 90 wedges, so 90 more wedges, 90 more, 90 more. So you get all 360 degrees, right? We call those little wedges, the amount, we call those degrees. And, but we have a more natural, I guess, way of expressing angle, and that is radians. And what I've seen is that a lot of AP Physics students have kind of forgotten what a radian is. And so let's make it really simple. You take the radius, here's the radius, and you cut it out, and you wrap the radius around. So if I took this distance, this length, made out of string or something, and I wrap that string around here, it would sweep out a certain angle. And that amount of angle is 1 radian. So a radian is the amount of angle you get when you sweep the radius around the circumference of that circle, 1 radius. And then, of course, you have 2, 3, 4. Of course, how many radii am I going to be able to wrap around this? 2 pi of them, or 6.1 or 6.24 something. All right, but that's how you think about what a radian is. 1 radian is basically is the angle you get when you sweep. You have 1 radius wrapped around the circumference. Okay, that's 1 radian of angle in there. Turns out, I'll keep the equal sign. It turns out that I believe 1 radian. What is it? I didn't calculate it. Is like 53 degrees or something like that. So you can easily figure it out. Well, by doing this, 2 pi radians is equal to 360 degrees. And so 1 radian, if I want to do the unit conversion, how many degrees is 1 radian? Because I'm sorry, I'm off screen. Tell me if I'm off screen. I'm zoomed in too much. So 1 radian. So, well, I know that 2 pi radians is 360 degrees. So the radians sort of cancel. Now remember that a radian is a ratio of 2 lengths. Let's say I want to know where this location is, in terms of radians. How many radians have I swept out? We'll measure this arc length around the circle, and we call that S, and divide it by the radius, and that'll be your number of radians. So theta in radians will be equal to S, that is this arc length, over R. This is going to be a big deal here pretty soon. We're going to use that for other stuff. So this will tell you what your answer is. What your angle is in radians. So let's just estimate it. Say 1 radius, 2 radius, maybe 2 2/3. I'd say that angle is probably like 2.7 radians. Just estimating, just counting how many radiuses do I have to get to that spot. Okay, so that's what a radian is. And so take your calculator, 360 degrees, divide that by 2 is 180, divide that by pi. Pi is 3.14, so it's a little less than 60 degrees. So what is that? Anybody help me out? Is it 57 degrees? 57.3 or 29? Yeah. So approximately 57.3 degrees, something like that, is 1 radian. Okay, and we're going to use that. So now, vectors are quantities, and they have a certain kind of mathematics to go along with them. So we're going to now, of course, we have scalars. And scalars, if you have a scalar is specified, in other words, you've completely described what it is by just giving a number and a unit. Like temperature. Okay. 67 kelvins. That's all you need to know what the temperature is. You say 67 kelvins. But if I say a position is 3 meters, I have not completely specified the location in space. I say 3 meters, what else do I need to give you? I need an angle. I need a direction. So scalars, this magnitude only, where vectors you need magnitude and direction. In other words, at least for a two-dimensional vector, which is what we're dealing with now, you need two pieces of information. You either need r and theta, or you need x and y. X and y, believe it or not, it doesn't give you a magnitude and direction, but you can figure out what the magnitude and direction are if I give you x and y. So that's enough. Yes?
Is there anything that's called like just a direction?
No. Not that I know of. Good question. I don't think so. There has to be something that's in that direction. So I don't know. Now, now, scalars is the kind of mathematics. All the mathematics you learn through elementary school and even mostly through high school. It's the mathematics of scalars, scalar quantities. But what we're going to do now is we're going to learn the mathematics, the arithmetic, really, of vector quantities, and it's different. Because I can, if you say, well, what is 3 plus 4 as a scalar? What is 3 plus 4 if you're dealing with scalars? 3 plus 4 is 7, right? But if it's a vector quantity, 3 plus 4 can be equal to 5. Get out. 3 plus 4 equals 5? Sure, because I'm not including the direction in those numbers. I was just giving you the magnitudes. 3 plus 4 can equal 5. That's what I'm talking about here. That we're going to deal with the arithmetic of vectors. So the first arithmetic we're going to learn is, before we get to that, how do you know when two vectors are equal? If let's say I have vector A. Does it equal vector B? Well, what specifies a vector? A magnitude and a direction. If they have the same magnitude and they have the same direction, they are equal. So if this is A, oops. I'm trying to draw these. Okay. And that's B. Okay, I'm desperately trying to make them the same. Okay? Then they are equal if they have the same. Now, notice what they don't have to have. They don't have to have the same starting point. You can pick up a vector and put it somewhere else, and it is the same vector. So if they, if you say, well, okay, let's do it this way. Let's say A has a magnitude of A and a direction of, I'll call it theta sub A. And B has a magnitude of B and a theta sub B. Okay? Now, look. If A and B, if the magnitudes of A and B are the same, and if this angle is the same as this angle, that is, they're parallel, I guess, then they are equal. We are saying that they are equal. We're defining those two vectors to be equal. Okay? Just kind of the way we decided to do it. Now, adding vectors. Well, this is, I'm really defining addition in a different way here. When you had scalars, if you have, 3 plus 4, okay, what did you do in first grade or kindergarten when you added 3 plus 4? The plus side says, hey, do this. Go 1, 2, 3, 4, 5, 6, 7, and that's your answer. Okay, so basically the plus sign when you're doing scalar arithmetic is saying count them all together. That's what addition means. That's what this plus sign is telling you to do. Now if I go A plus B, all right, the plus sign means something different now. It's not saying, count them together, because what are you counting? No, it says hook them up head to tail and figure out what you get. Okay, so let's say A looks like this. and B looks like this. So if I want to know what do I get when I go A plus B, well, what you do is what this plus sign says to do, hook them up head to tail. Put the A right here. I can pick vectors up in my imagination. Right like that, see? Isn't that amazing? Now pick up B. Where am I going to put it? You start B where you ended A. So don't hook them up tail to tail. It's head to tail. This is called the head, and this is the tail. So B will go right here. What is my answer? My answer, my resultant vector, well, you start where A started and you end where B ends. And I put an arrowhead on it. I'm going to call that big R. That's the result of adding those two vectors together. You hook them up head to tail. You follow that procedure. And by the way, it works for not just two vectors when you're adding, but if you're adding three vectors, you hook them up head to tail, head to tail, head to tail. And you start where the first one started, you end where the last one ends. And that's your answer. That's your resultant vector. Now this makes a lot of sense, right? If I'm going to add displacement vectors, for example, if I say, okay, walk 3 meters this way and then 4 meters that way, well, where are you going to end up? You're going to end up 5 meters from where you started, right? The 3, 4, 5 triangle, If A and B are perpendicular, that works. And so, in other words, the plus sign here is a procedure. It's saying, hey, do this to these two guys. Do what? Add them up, head to tail. Well, now, what about B plus A? Okay, well, you start with B. Add A to it. And so here's B plus A. And there's my result. There's my resultant vector. Boy, doesn't that look the same? Oh, that's because it is. If I just put a B plus A, here's B, and here's A. If I just added that, they'll get to the same spot. So this is the property of addition of vectors. It's called the Commutative Law of Addition for vectors. That is, A plus B equals B plus A. Okay. Now, if I have three vectors, A plus B plus C, it works the same way. Okay, let's go A plus B plus C equals R. Well, let's make up a vector. Here's A, here's B, here's C. I'm just making these up. First of all, I think you can see if you just kind of practice with this, if I just go, okay, A plus B plus C. Okay, I just added them up and I got, let's see, did I do that right? Yeah.
It's a label that little R.
Yeah, oh yeah, I just didn't finish. My pencil's getting like some wood right there, and so it's not writing. So here's A, B, and C like that. Well, what if I think we already covered it. It doesn't matter what order you add these in. But what if I say, well, let's add up A plus B first, and then add C to it. If I add A plus B first, I get this guy. There's A plus B. And then if I add C to it, I'll get my resultant. So this is the associative property. It basically says, hey, if you're going to go A plus B plus C equals R, if you want, you can add A plus B first and get another vector and then add c to it, and it won't change your answer. And if you draw these goofy little pictures like this, it's easy to understand these properties. So we have the commutative property, we have the associative property, so that's great. Now, let's define what is a negative vector. We have negative scalars, right? So what is a negative vector? Right, same magnitude, opposite direction. That's exactly what it means. Same magnitude, opposite direction. Okay, that's a negative vector. So if this is A, then this is negative A. Just make the vector in the opposite direction. Now, why do we need to define that? Well, because we're going to have vector subtraction. And if I subtract vectors, what if I've got A minus B? So, like, here's A, here's B, but I want to subtract these vectors. Well, here's the subtraction operator in vector arithmetic. It means do something a little different. It's a little different than scalar. It says, hey, change this, just make it A plus negative B. So this is kind of the definition of what vector subtraction is. Hey, take the second one, and we're going to add the opposite. Right? I think he did this in my son's in the 7th grade right now, and he's doing this with integers. Right? They're doing negative integers, and whenever you add subtraction, remember you add the opposite. You change both things. Well, that's exactly what we're doing here. But what we mean by a negative vector just means, hey, put it in the opposite direction. So now I'm going to take, here's A. Now, what am I going to do? I'm going to add negative B. Well, what is negative B? It's this. There's negative B. So I'm going to take that and add it to this. So here's A. Here's negative B. So my result, right here, this is A, this R right here is A minus B. This is my answer. From starting where A started and ending where negative B ended. That's A minus B. Oh, by the way, notice that the commutative property doesn't work here. What if I went B minus A? Am I going to get the same answer? Not at all. Let's put here's positive B, and again you can check all of these really easily just by drawing a little sketch. Here's B. Now what is negative A? We're going to add negative A to it. So this is B plus negative A. So here's negative A. It's down like this. So here's B, here's negative A, and here's my answer. And look, you see a relationship between this answer here and this here? Yeah, it's going to be the same answer in terms of magnitude, but the direction is opposite. So basically, if you switch them, you're going to get the same answer. But now that's true. Like what is 4 minus 7? 4 minus 7 is negative 3. What is 7 minus 4? It's positive 3. So it's the same kind of idea. You get the same magnitude, but opposite in direction or opposite in sign. Okay? So that's vector subtraction. Oh, last thing, we're going to talk about multiplying vectors by a scalar. So we're going to multiply, this is the last thing, multiply vectors by a scalar. Now, hey, there's several kinds of multiplication when you have vectors. Like with scalars, there's one kind of multiplication. With vectors, there's three kinds of multiplication. There's when you multiply two vectors together and you get a scalar answer. There's when you multiply two vectors together and you get a vector as an answer. And then you multiply a scalar and a vector together. And that's what we're going to talk about here. If I say 3 times a, 3 is a scalar. There's my scalar. And I'm going to multiply it by vector a. So it's pretty easy. If this is vector a, well, this is going to be equal to a plus a plus a, right? So a plus a plus a. Well, there's 3a. There's my answer right there. So all you're doing is multiplying. And this doesn't have to be a positive integer. This can be anything. You just multiply. You can go 2.5. So you go 1, 2, and then half of. So it can be fractional. It can be negative. What happens if you multiply it by a negative? It's just changing the direction now. Okay, so if you multiply it, say negative 3a's. Oh, okay, well, I'm going to go negative a plus negative a plus negative a. There's my answer. Okay, so you've got a lot of problems to practice, these ideas. If they tell you to solve something graphically, you may need to use a protractor and a ruler and make a scale drawing of it. So if you don't have a protractor to measure angles with, I suggest you stop by, Walgreens or something and get one. And I'm not endorsing Walgreens, okay? Any store, right, that'll have. I don't want to get sued, by Walmart or some Wally. I want to start a store called Wally. All right. Anyway, that is all.